A massive stone block, weighing more than 50 tons, sits perfectly in place without a drop of modern mortar. This is the reality of ancient engineering. The structural genius of our ancestors created monuments that stand defiantly against time, and we are going to uncover how they achieved the impossible. By the end of this journey, you will understand the hidden principles that allowed civilizations with simple tools to outperform our modern expectations. We will investigate how the Great Pyramid was aligned with the stars using technology we can barely comprehend, and how entire cities were carved directly into mountain faces. What forgotten knowledge do you believe is still waiting to be rediscovered in these ancient stones? This deep understanding of the world did not appear overnight. It was a slow and careful accumulation of knowledge passed down through generations of keen observers. These master builders were the original scientists, conducting a lifelong study of the materials beneath their feet and the skies above their heads. They learned to read the landscape, identifying the strongest stones and the most stable foundations by sight and touch. They watched how water shaped valleys over centuries and understood how wind could gradually wear down even the hardest granite. This intimate connection with nature's raw power informed every decision long before any construction began. Their tools were simple, but their methodology was incredibly advanced. They developed complex mathematical systems to calculate weight, stress, and angles, performing these intricate equations with ropes, pegs, and an intuitive grasp of geometry. The placement of the Great Pyramid, for example, is not merely aligned with the North Star. Its sides are oriented to the 4 cardinal directions with an accuracy that rivals what we could achieve with modern satellite technology. How did they achieve such precision with what we would consider primitive instruments? They used the world itself as their guide, tracking the shadows cast by the sun and the consistent paths of specific stars. This empirical approach, testing ideas through direct observation and repeated practice, formed an unshakable foundation for their work. They turned raw, unpredictable nature into a reliable partner, building not in spite of the environment, but in perfect harmony with it. This profound connection with nature extended directly into the materials they chose. The very stones they selected were far more than simple building blocks. They were active partners in the construction process, each type chosen for its unique personality and strength. Ancient engineers possessed an almost intuitive understanding of geology, knowing that a limestone from one quarry could bear a different load than the same stone from another. They learned to read the grain of granite, to sense the hidden fractures in sandstone, and to identify the most durable timber by its scent and weight. This was not guesswork, it was a deep, empirical science born from generations of observation and hands-on experience. Consider the colossal granite obelisks of Egypt. Quarrying a single 100-foot monolith was a monumental undertaking. Workers would meticulously drill a line of holes along the intended fracture line, then drive dried wooden wedges into them. When these wedges were soaked with water, they would expand with incredible force, cleanly splitting the rock along a perfectly straight line. This technique required a precise knowledge of the stone's internal structure. A miscalculation could shatter the entire block, wasting months of labor, but their mastery did not end at the quarry. Transporting a 50-ton stone obelisk across hundreds of miles of desert was a logistical puzzle that would challenge modern engineers. They did not have the wheel in a practical form for such loads, so they invented their own solutions. They likely slid these giants on wooden sledges across lubricated pathways of wet clay, a method that drastically reduced friction. How many workers did it take to pull such a sledge? We can only estimate, but the organization and coordination required was a feat of social engineering as much as it was mechanical. This material wisdom reached its zenith with the Romans, who developed a form of concrete that seems to defy the ages. Their recipe, a mixture of lime, volcanic ash, and small rocks, created a chemical reaction that actually strengthens over time, especially when exposed to seawater. While our modern concrete can crumble after 50 years, Roman piers still stand strong after 2000, enduring the constant pounding of waves. They understood the principles of compressive strength, designing arches and domes that channeled weight downward, allowing massive structures like the Pantheon to remain the world's largest unreinforced concrete dome for centuries. Their buildings were not just made to stand, they were designed to become a permanent part of the landscape, to withstand the tremors of the earth and the slow, patient erosion of wind and rain. They chose their materials not for convenience but for permanence, creating a legacy written in stone and mortar that continues to whisper its secrets to us today. This material wisdom found its ultimate expression in the language of mathematics, a universal code etched directly into stone. Ancient builders understood that geometry was far more than an abstract science. It was the invisible framework that gave their structures both unshakable strength and breathtaking beauty. Look at the Parthenon standing atop the Acropolis in Athens. At first glance, it appears as a structure of perfect straight lines and right angles, but this is an illusion, a masterpiece of intentional imperfection. Every single line in the Parthenon is actually a subtle curve. The base bows upward in the center, the columns lean inward, and each one swells slightly. Why would engineers go to such incredible trouble? They were correcting for the human eye. They knew that truly straight lines would appear to sag from a distance, so they built in these gentle curves to create the visual impression of perfect rigidity. This was engineering that accounted for human perception, a marriage of mathematics and psychology carved in marble. This pursuit of perfection was governed by mathematical ratios, most famously the golden section. This divine proportion, a ratio of approximately 1.618 to 1, appears repeatedly in nature, from the spiral of a nautilus shell to the arrangement of seeds in a sunflower. The ancients saw this pattern as a fundamental law of aesthetic harmony, and they embedded it into their greatest works. When you look at the facade of the Parthenon, its dimensions fit almost perfectly within a golden rectangle. This ratio, consciously or intuitively applied, creates a sense of balance and order that we find inherently pleasing, but it was not merely about beauty. These same proportional principles are key to structural integrity. A wall built with golden ratio proportions naturally distributes stress more evenly, making it more resilient to forces like wind and tremors. The mathematics that pleased the eye also fortified the stone. This geometric language was not confined to a single culture. From the precise grid layouts of Mohenjo-Daro in the Indus Valley to the celestial alignments of Teotihuacan in Mesoamerica, a common understanding of space and proportion emerges. The Romans used geometry to lay out their vast networks of roads, arrows straight for miles, and to design aqueducts that maintained a precise, gentle slope across impossible distances, bringing fresh water to entire cities. This was a global phenomenon, a shared intellectual toolkit that allowed disparate civilizations to solve similar problems. They were all reading from the same cosmic blueprint, using ropes and stakes to translate celestial order and natural proportion into the physical world. Their monuments are not just piles of rock, they are frozen equations, a silent testament to a time when the line between an artist, an engineer, and a mathematician was beautifully and intentionally blurred. What other profound connections between number and nature are we still learning to see in their enduring legacy? That silent geometric language finds its ultimate expression in the sands of Giza. The Great Pyramid stands not merely as a tomb, but as a mountain of data, a perfect storm of engineering precision that defies simple explanation. Its base forms a near-perfect square, with sides leveled to within a fraction of an inch across an area larger than 10 football fields. How could ancient surveyors achieve such flawless flatness using only water-filled trenches and the sun's shadow? The orientation is even more astounding. Its sides are aligned to the 4 cardinal directions: north, south, east, and west, with an error of less than 1/15 of a single degree. This is an accuracy that rivals what we could accomplish today with GPS satellites and laser theodolites. They were not just building with stone, they were aligning a monument with the very axis of the planet itself. Inside this colossal structure, the precision only deepens. The internal chambers and passageways, like the Grand Gallery and the King's Chamber, were built from massive granite blocks, some weighing over 50 tons. These were hauled to the heart of the pyramid and positioned with gaps between them often less than the thickness of a human hair. This was not just for aesthetic appeal. This meticulous craftsmanship was fundamental to the pyramid's structural integrity, distributing the unimaginable weight of the millions of limestone blocks above. The question of how they moved these stones remains one of history's greatest puzzles. The most accepted theory involves a massive, spiraling ramp built against the pyramid's rising sides, a temporary mountain of earth and brick used to drag the blocks upward. Yet, other compelling theories suggest sophisticated counterweight systems, or even the use of water channels to float the stones on barges through temporary locks. Each block placed was a triumph of logistics and brute force, a testament to a society that could organize thousands of workers with the efficiency of a modern corporation. The pyramid's enduring form, still standing after millennia of desert winds and seismic tremors, is a direct result of this obsessive attention to detail. Its shaped channels weight downward and outward, allowing it to settle without collapsing. The Great Pyramid does not just inspire awe with its scale, but with its mind, a frozen moment of mathematical and engineering genius that continues to challenge our understanding of what is possible. While the pyramids stand as monuments to the divine, Roman engineering was a testament to the practical, bringing life-giving water across impossible landscapes. The aqueduct was not merely a structure, it was a river tamed, a constant flowing artery that enabled an entire empire to thrive. To achieve this, Roman engineers mastered the gentle, unyielding power of gravity. They designed these channels with a precise, continuous downward slope, often as little as a few inches per mile, allowing water to flow effortlessly from distant mountain springs directly into the heart of bustling cities. This required an astonishingly accurate understanding of topography, mapping the land's contours over distances that could stretch for 50 miles or more. How did they maintain this perfect gradient across deep valleys and rocky gorges? The answer lies in one of their most enduring innovations, the arch. By constructing towering arcades of arches, they could carry the water channel high above the ground, maintaining its critical slope across any obstacle. The arch is a perfect example of their structural genius, channeling the immense weight of the stone and water downward and outward into the sturdy piers, creating a form that is both incredibly strong and remarkably efficient with materials. Nowhere is this elegant power more visible than at the Pont du Gard in southern France. This colossal three-tiered aqueduct bridge strides across a wide river valley, its majestic yellow limestone blocks fitted together without any mortar. The tallest arches soar nearly 160 feet high, a breathtaking lattice of stone that has withstood 2,000 years of floods and weather. It was not built for glory but for pure function to deliver water to the city of Nemesis. This was the hidden machinery of the Roman world, a network of channels, tunnels, and bridges that worked in silent unison. The water they carried did more than just quench thirst. It powered grain mills for baking bread, supplied fountains that cooled public squares, and fed the vast public baths that were centers of social and civic life. The aqueduct was the ultimate symbol of Roman order, a concrete manifestation of their ability to reshape the world to their will, not with brute force alone, but with a deep and unshakable understanding of the silent laws that govern our physical world. While the aqueducts demonstrated Roman mastery over horizontal distance, the Pantheon in Rome represents their conquest of vertical space. Its dome is not merely a roof, it is the sky itself captured in concrete. For over 1,800 years, this magnificent structure has held the title of the world's largest unreinforced concrete dome, a record of endurance that modern engineering has yet to break. The sheer scale is humbling, a perfect hemisphere spanning 142 feet, resting upon walls 20 feet thick. To stand beneath it is to experience a profound sense of awe, a feeling the builders intentionally crafted. The dome's secret lies not in its mass but in its intelligent lightness. As the dome rises, its composition changes. The heavy, dense concrete at the base, mixed with travertine and tufa, gradually gives way to a lighter mix at the summit, incorporating porous volcanic pumice and even empty clay amphorae. Think of it as a carefully layered cake, with the heaviest ingredients at the bottom and the lightest at the top. This brilliant gradation dramatically reduced the overall weight and the downward thrust on the supporting walls, preventing the structure from collapsing under its own immense load. But the most breathtaking feature is the oculus, the great circular opening at the very center of the dome. This 27-foot wide eye to the sky is far more than a dramatic source of light. It is a critical structural component. By removing the heaviest, most unstable part of the vault, the oculus eliminated the point of greatest stress, allowing the dome to settle and breathe as a perfect, continuous ring. Rain and snow fall through this opening, draining away through a nearly invisible network of channels in the marble floor, a system that has functioned flawlessly for 2 millennia. How could such a vast, unsupported span of ancient concrete withstand earthquakes, invasions, and the relentless passage of time? The answer is in the Roman genius for holistic design. The dome, the walls, and the foundation were conceived as a single, unified system. The thick rotunda walls contain a series of hidden voids and arches that channel stresses downward, while the concrete itself, with its magical volcanic ash recipe, grows stronger over centuries as it continues to cure. The Pantheon is not a building that has simply survived. It is a building that is still actively working, a living testament to an engineering philosophy that saw no distinction between the strength of a material and the elegance of its form. It challenges us to reconsider what we mean by permanent, offering a silent, enduring lesson from the heart of the ancient world. Far to the south, in the heart of the Andes, another civilization wrote its own chapter in the book of structural genius. Here, the challenge was not just gravity, but the very ground itself, which could shudder and shift without warning. The Inca response was not to fight this movement, but to build in harmony with it, creating walls that could dance with an earthquake. They achieved this with a technique of almost unimaginable precision, fitting massive, irregular stones together so perfectly that the seams between them vanish. You cannot slide the edge of a knife or even a single piece of paper into the joints of the finest Inca walls. This is ashlar masonry, and its purpose was not mere beauty but brilliant seismic resilience. At sites like the mountaintop citadel of Machu Picchu and the monumental fortress of Sacsayhuaman, you see walls composed of polygonal stones, each one a unique, interlocking puzzle piece. Some of these granite blocks are colossal, weighing many tons, yet they were shaped and polished to fit their neighbors with microscopic accuracy. How did they achieve such perfection with only stone hammers and bronze tools? It was a patient, generations-long process of trial and observation. The builders understood that a wall built with rigid, uniform blocks and brittle mortar would crack and crumble when the earth shook. Their solution was a flexible, living wall. During a tremor, the intricately shaped stones in an Inca wall would shift and jostle against each other, the energy of the earthquake dissipating as friction between the countless interlocking faces. When the shaking stopped, the stones, locked by their own unique geometries and the immense weight of the structure, would simply settle back into place. It is a system that functions like a three-dimensional jigsaw puzzle made of granite, possessing both the strength to support immense weight and the flexibility to absorb catastrophic force. This required a profound, intuitive knowledge of geology, understanding how different types of stone would fracture and wear, and a masterful grasp of mechanics, knowing exactly how to distribute stress across a complex, non-repeating pattern. Their architecture was a dialogue with the landscape, a conscious decision to build with the rhythm of the earth, not against it. In a land defined by tectonic power, they found a way to make stone itself resilient, creating a legacy that clings to the mountainsides, silent and steadfast, as if it had grown there from the very beginning. This pursuit of perfect balance found another profound expression in the sun-drenched sanctuaries of ancient Greece. The Greek temple was conceived as a mirror of the cosmos, a place where mathematical harmony and spiritual reverence became one and the same. At first glance, its form seems straightforward, a simple post and lintel system of vertical columns supporting horizontal beams. Yet every single line was a carefully calculated deception, designed to appear perfect to the human eye. The most famous of these subtle tricks is a gentle swelling in the columns known as entosses. If the columns were built perfectly straight, they would appear to curve inward from a distance, creating a weak, sagging illusion. To counter this, the builders gave each column a slight, almost imperceptible convex curve, making it look perfectly straight and robust from every angle. This was not a structural necessity, but a psychological one, an act of engineering that accounted for human perception to achieve an ideal of divine perfection. The columns themselves taper as they rise, further enhancing this sense of soaring height and stability. This meticulous attention to visual effect is perfectly preserved in the Temple of Hephaestus in Athens. Its Doric columns, standing in quiet dignity, demonstrate how this system effectively distributed immense loads. The weight of the massive stone lintels and the entire roof structure was channeled directly down through the vertical columns into the sturdy platform below. This created a stable, balanced framework of incredible strength, one that has withstood earthquakes for over 2,000 years. But why go to such extraordinary lengths? For the Greeks, beauty was not separate from function, it was the highest form of it. A temple was the dwelling place of a god, and its architecture had to reflect the flawless order of the divine realm. The proportions of the structure were often governed by sacred ratios, creating a space that felt inherently right and harmonious to those who entered. It was a space designed to elevate the human spirit, using the silent language of mathematics and the enduring strength of stone. In these hallowed spaces, the engineer served the priest and the quarryman served the artist, all united in a single goal: to build a doorway to the heavens that would stand forever. But what happens when this structural genius is applied not to stone, but to life itself? The legendary Hanging Gardens of Babylon represent the ultimate fusion of engineering and nature, a living mountain of greenery built in the heart of a desert metropolis. Ancient writers describe a breathtaking vision, a ziggurat of terraced gardens rising into the sky, overflowing with trees, vines, and exotic flowers. This was not a simple garden. It was a multi-level ecosystem, an artificial hill sustained by a hidden mechanical heart. The greatest challenge was not holding the soil on those soaring terraces, but quenching its thirst. In the arid climate of Mesopotamia, supplying enough water to keep the entire structure lush would have been a monumental task. The solution was a feat of hydraulic engineering that seems to defy its era. Historical accounts suggest a complex system of chain pumps, a continuous loop of buckets mounted on a spinning wheel, powered either by laborers or perhaps by the flow of the Euphrates River itself. This device would have lifted water from the river below, channeling it to a reservoir at the very top of the gardens. From that high point, a network of canals and smaller channels would have allowed the water to cascade downward from terrace to terrace, nourishing every root and saturating every layer of soil. This would have been one of the earliest applications of hydroponic principles, a way to cultivate plants without relying solely on natural rainfall. The structural support for such a heavy, waterlogged environment would have been just as advanced. The terraces were not mere dirt piles. They were likely intricate sandwiches of materials, with layers of reeds and bitumen for waterproofing, topped with deep beds of fertile soil, all supported by vast, arched brick vaults strong enough to bear the immense shifting weight. The entire creation was a paradox, a lush, vibrant forest that was entirely man-made, a testament to a civilization that sought to reshape its environment not just for grandeur but for beauty. Whether the gardens were a physical reality or a powerful amalgamation of different engineering marvels into one ideal, their enduring legend challenges our perception of ancient limits. They stand in our imagination as the ultimate symbol of a lost world where engineers did not simply conquer gravity with stone, but dared to make the desert bloom. The challenge of an Egyptian obelisk began deep within the earth, in the granite quarries of Aswan. Here, workers faced a single, unbroken piece of stone destined to become a 500-ton needle pointing to the sun. Their tools were deceptively simple, yet their methodology was brutally effective. To separate the monolith from the bedrock, they did not use chisels in the traditional sense. Instead, they pounded the granite with balls of dolerite, a stone even harder than granite, while pouring abrasive quartz sand into the deepening groove. This combination of pounding and grinding slowly, relentlessly, wore a channel through the stubborn stone. This was not a quick process. It was a testament to immense patience and a deep understanding of material science, using the very hardness of the earth to sculpt it. Once free, the rough obelisk was then shaped and polished to a mirror finish, its surfaces carved with intricate hieroglyphs that would tell its story for millennia. But carving it was only the first impossible task. Moving this slender giant from the quarry to its sacred destination was a logistical nightmare. The solution was the Nile itself. During the annual flood, when the river swelled and reached its highest point, engineers would dig canals directly to the base of the waiting obelisk. They would then carefully maneuver it onto a massive, purpose-built barge, a vessel of such size and strength it was essentially a floating fortress. The river's current and the coordinated effort of teams of rowers would then carry this incredible load hundreds of miles downstream. Imagine the sight of that barge, a mountain of stone gliding silently through the water, a feat that would be impressive even with modern technology. The final, most perilous act was its erection. At the temple site, workers would have prepared a steep ramp leading down to a foundation pit. The obelisk, still on its side, would be slowly, incrementally, pulled up the ramp until its base was positioned directly over the hole. Using a complex system of ropes, levers, and counterweights, crews would then begin the delicate process of tilting the monolith upward. This was the moment of greatest risk, a heartbeat where a single slip could shatter a decade of work. As the stone pivoted, its base would slide into the waiting foundation, settling into a socket packed with sand. This sand could be carefully removed from side chambers to make micro-adjustments, ensuring the obelisk stood perfectly vertical. Once upright, it was more than a monument. It was a conduit, a physical connection between the pharaoh and the sun god Ra, its gleaming capstone catching the first and last light of each day. Each obelisk was a declaration, written in stone, that humanity could not only shape the earth but could lift its very essence toward the heavens. That same Roman genius for monumental scale found its ultimate public expression in the roaring heart of the empire, the Colosseum. Rising from the ground, its skeleton was a masterpiece of repetitive strength, a vast ellipse of 80 arched entrances, but this was far more than a beautiful facade. Each of those arches was a crucial component in a brilliantly efficient structural system, channeling the colossal weight of 50,000 spectators down through 3 tiers of vaulted passageways and into the massive foundations below. This intricate web of stone created a structure that was both incredibly strong and remarkably open, allowing immense crowds to enter and exit with a fluidity that modern stadiums still strive to emulate. Beneath the wooden arena floor lay an entirely separate world, the Hypogeum. This subterranean labyrinth of tunnels and chambers was the backstage engine of the spectacle. Here, a complex system of ramps, pulleys, and counterweighted elevators operated in near darkness. Caged animals, elaborate stage sets, and combatants could be lifted through hidden trapdoors directly onto the arena floor, creating dramatic and surprising entrances that thrilled the crowds. This was ancient stagecraft powered by pure engineering, transforming the arena into a dynamic theater of the unexpected. The exterior facade told its own story of layered intelligence. The 3 levels of arches were framed by columns, each tier featuring a different architectural order. The sturdy, simple Doric style on the ground floor gave a sense of solidity. The more ornate Ionic columns on the 2nd level added grace, and the elegant Corinthian capitals on the 3rd provided a crowning flourish. This was not merely decorative. It was a visual expression of load-bearing, with the heaviest-looking style at the base and the lightest at the top, creating a sense of stable, upward progression that pleased the eye and calmed the mind. The materials chosen were a testament to their practical wisdom. The exterior was clad in tough travertine limestone, able to withstand the elements, while the immense inner vaults were constructed from lighter, volcanic tuff and a revolutionary Roman concrete that could be poured into complex shapes. This combination of material science, structural daring, and crowd management created a blueprint for the world. The Colosseum's fundamental design, an oval bowl with tiered seating and multiple access points, has been echoed in sports arenas and theaters for 2,000 years. It stands as a powerful reminder that Roman engineering was never just about making things big, but about making them work perfectly for the people who used them. While the Romans built their water highways above the ground, another civilization mastered the art of finding rivers hidden deep within the earth. In the vast, sun-scorched plateaus of ancient Persia, survival depended on a different kind of genius, one that worked in cool, silent darkness. The Persian Qanat was not a grand bridge or a towering aqueduct, but a gently sloping tunnel, a man-made vein that reached deep into the foothills of mountains to tap distant, subterranean water. This was not merely digging a well, it was a precise and daring form of hydrological surgery. Engineers would first identify an aquifer, a layer of water-bearing rock, often at the base of a mountain range where rainfall had percolated down through the stone. From this mother well, they would begin carving a tunnel, sloping ever so slightly downward, just enough for gravity to pull the water along its course. The gradient was everything, a drop of perhaps only 1 meter for every kilometer of tunnel, too steep and the water would flow too fast, eroding the channel walls. Too flat and the life-giving current would simply stall. How could they maintain such a perfect, gentle slope across miles of uncharted earth without any modern instruments? They used simple, brilliant tools. A long, water-filled trench acted as a level, while hanging plumb bobs and sighting poles allowed them to chart a straight and true course through the rock and soil. But the true signature of the Qanat, dotting the desert landscape like a line of ancient craters, were the vertical access shafts, dug at regular intervals, sometimes every 20 meters. These shafts served a dual purpose. They provided air for the tunnel diggers working far below, and they were crucial for removing the excavated material, hauled up in buckets by teams of workers. These shafts also became permanent features, allowing future generations to descend and perform the vital maintenance that kept the water flowing for centuries. The impact of this invisible network was profound. A single Qanat could transform a barren valley into a fertile oasis, supporting farms, villages, and eventually great imperial cities of the Achaemenid Empire. This was sustainability engineered for the long term. Unlike a surface canal, which loses vast quantities of water to evaporation under the desert sun, the Qanat protected its precious cargo in a subterranean world, delivering it cool and clean directly to where it was needed. It was a system that respected the limits of the environment, a legacy of patient, communal effort that turned the most unforgiving landscapes into cradles of civilization. Its brilliant light was a star fixed upon the earth, a beacon for every ship navigating the treacherous waters of the Nile Delta. The Lighthouse of Alexandria did not merely stand, it presided, a colossal white tower of marble and limestone soaring to a height that may have reached 400 feet. For centuries, it was one of the tallest man-made structures in the world, a guiding hand stretched out from the shore. By day, its secret weapon was not the flame, but a massive, polished bronze mirror. This mirror could capture the Mediterranean sun, focusing its rays into a blinding signal visible far out to sea, a gleaming pinpoint of reflected daylight that cut through the haze. When darkness fell, the mirror was pivoted, and a great furnace at the summit was stoked, its fire amplified and projected by the same reflective surface into a powerful, sweeping beam. This was not a simple bonfire on a hill. It was an ancient optical system, a sophisticated combination of fire and physics that transformed maritime navigation. The logistical challenge of keeping this signal burning was immense. How did they transport the enormous quantities of wood or other fuel required to feed a perpetual fire at such a dizzying height? The most compelling theory points to a wide, spiraling ramp that corkscrewed its way up through the tower's core. This internal roadway would have allowed teams of donkeys or oxen to haul carts of fuel directly to the summit, a continuous supply line that ascended inside the very monument it served. This design speaks to a profound understanding of practical needs, where grandeur was always married to function. The lighthouse's endurance was as remarkable as its light. It stood defiant against the elements for over 1,600 years, surviving a series of powerful earthquakes that would have leveled lesser structures. Its resilience was rooted in its robust, intelligent design. The foundation was built upon a massive base of stone blocks, some of them likely submerged to counteract the shifting sands of the coastline. The tower itself was not a solid pillar, but a hollow shaft with a central core, a design that provided both structural stability and the internal space for that crucial ascending ramp. The choice of light-colored stone was also strategic. making the tower highly visible against the blue sea and sky during daylight hours. More than a navigational aid, the lighthouse was a potent symbol of Hellenistic ambition, a declaration that human intellect could master both the sea and the sky. It blended raw, elemental power with elegant architectural form, a perfect fusion of engineering and art that guided sailors safely home long after the civilization that built it had faded into history. While the Egyptians reached for the sun and the Romans mastered water, in the land between two rivers, humanity built its first mountains to the gods. The Mesopotamian Ziggurat rose from the flat alluvial plain like a stairway carved for deities, a colossal stepped pyramid of mud brick that dominated the spiritual skyline. Its core was humble, sun-dried bricks made from the very earth of the riverbanks, but its ambition was celestial. This core was ingeniously reinforced with layers of woven reeds and bitumen-coated mats, a flexible internal skeleton that absorbed the stresses of settling and seismic shifts, preventing the massive earthen structure from simply crumbling under its own weight. The entire structure was then sheathed in a protective skin of kiln-fired bricks, a waterproof armor that defied the rare but torrential rains. The most defining feature was the ascent, a series of steep external staircases or ramps that climbed the tiers in a zigzag pattern, a ritual pathway that mirrored the difficult journey toward the divine. At the summit, far removed from the mundane world below, stood a small, exquisite temple, the dwelling place of the city's patron god. This was not a public space, but a sacred precinct where priests alone could commune with the heavens. The partially restored ziggurat of Ur still whispers of this grandeur, its massive footprint and three towering tiers a testament to a society that could mobilize thousands of workers not for a pharaoh's tomb, but for a collective act of faith. The logistics were staggering, requiring the production of millions of identical bricks, the organization of skilled laborers and unskilled conscripts, and a master plan that could coordinate the entire decades-long project. This was more than architecture, it was a physical prayer, a statement that even in a world of clay and reeds, human beings could engineer a connection to the infinite, laying the foundational stones of civilization itself with every course of brick they laid. Buried in silent, subterranean battle formation for over 2,000 years, an entire army of clay stands ready. The Terracotta army of China's first emperor is not a collection of identical statues, but a breathtaking display of mass production on a scale the ancient world had never seen. Each of the thousands of soldiers, from the lowliest infantryman to the highest-ranking general, possesses a distinct face, a unique personality frozen in fired earth. This incredible individuality, however, was born from a brilliantly systematic and modular process. Artisans did not sculpt every figure from a single block of clay. Instead, they operated like a highly organized factory, producing a limited set of standardized parts. Legs, torsos, arms, and heads were created in separate workshops using molds. This assembly line approach allowed for rapid production, but the true genius emerged in the final assembly. Once the basic components were joined, master craftsmen stepped in. Using their hands and simple tools, they added layers of wet clay to sculpt individual facial features, hairstyles, and expressions. They carved intricate details into armor and carefully shaped hands to hold specific, now vanished weapons. This hybrid system combined the efficiency of mass production with the artistry of custom craftsmanship, resulting in an army where no two soldiers are exactly alike. The manufacturing challenge did not end with sculpting. How do you fire a life-sized clay figure without it cracking or exploding in the kiln? The engineers solved this with remarkable technical skill. The figures were constructed with hollow torsos and solid legs to provide a stable base. Small, carefully placed vent holes were incorporated to allow steam and gases to escape during the intense firing process, which reached temperatures exceeding 900 degrees Celsius. This precise control of the kiln environment transformed the soft clay into incredibly durable terracotta, a material strong enough to survive for millennia. The logistical puzzle extended to deploying this ceramic army. The figures were arranged in battle formation within massive, underground pits. These were not simple holes in the ground, but complex, architecturally designed spaces. Strong, rammed earth walls were built to partition the pits into different corridors, while the entire complex was covered with a vast roof of heavy wooden beams, mats, and layers of packed earth. This structure protected the army, concealing it from view and bearing the immense weight of the world above. The entire project, from quarrying the clay and fueling the kilns to coordinating thousands of artisans and laborers, represents a staggering feat of administrative organization. It was a monumental undertaking of supply chain management and quality control, a silent testament to an empire that had mastered the art of large-scale project coordination, creating a permanent garrison not of flesh and blood, but of earth and fire. High on the arid plains of southern Peru, a vast canvas of desert stone holds secrets only visible from the sky. The Nazca lines are a gallery of giants, a collection of massive geoglyphs depicting spiders, hummingbirds, monkeys, and geometric forms stretching for miles across the plateau. These are not monuments built upward, but art carved downward, created by the meticulous removal of the dark, oxidized gravel that blankets the land, revealing the stark white gypsum-rich soil beneath. This simple yet profound technique created a visual contrast that has endured for over 2,000 years, preserved by one of the driest climates on Earth. The true engineering marvel, however, lies not in the making of a single line, but in the execution of a perfect, colossal shape. How could artists and surveyors, standing at ground level, create a hummingbird with a wingspan of 200 feet, whose every curve is flawlessly proportioned? They could not see their own work. The entire design existed only in their minds and in their precise, scaled plans, translated to the desert floor through an astonishing feat of geometric projection. Using a system of stakes and ropes, they would have plotted key points and then connected them with unwavering straight lines, clearing the rocky surface along these predetermined paths. The sheer scale required an intimate knowledge of measurement and an ability to maintain direction across vast, featureless distances. This was large-scale drafting without the benefit of an aerial view, a testament to a culture that could hold a complex image in their collective imagination and then walk it into existence across the face of the earth. The purpose of these immense drawings continues to spark debate. Were they a celestial calendar, their forms aligned with stars and solstice points, or were they ritual pathways walked by priests during sacred ceremonies to call upon the gods for water in this unforgiving landscape? Perhaps they were offerings meant to be seen not by people, but by deities in the sky above. Whatever their intention, the lines demonstrate a masterful command of their environment. The creators understood that by merely disturbing the top layer of dark stones, they were creating a design that would be naturally maintained. The lack of rain meant the lines would not wash away, and the unique atmospheric conditions of the Nazca plain prevented the dark patina from quickly reforming. They engineered these geoglyphs to be permanent features with an almost passive resilience, using the desert's own stable nature as their preservation tool. In this, the Nazca lines represent a different kind of structural genius, one that manipulated the surface of the world not to withstand forces, but to become a permanent, silent message to the heavens. On a remote island in the vast Pacific Ocean, silent giants stand guard over an empty landscape. the Moai of Easter Island are a profound mystery carved in volcanic rock. Each of these colossal statues was quarried from the slopes of the Rano-Raraku volcano, a soft volcanic tuff that allowed for detailed carving. The scale is staggering, with some figures standing over 30 feet tall and weighing more than 80 tons. Yet the quarry is miles away from the coastal platforms where the Moai were meant to stand. How did a society with no wheels, no metal tools, and no large animals to provide draft power move these monolithic figures across kilometers of rugged terrain? One compelling theory suggests the islanders used the statue's own weight against itself. By carefully rocking a Moai from side to side with ropes, teams of workers could create a walking motion, inching the giant forward in a slow, controlled wobble. This method of upright transport would have been a delicate dance of coordination and strength, a rhythmic effort that left the statues partially supported by their own momentum. An alternative idea involves a more grounded approach, laying the Moai on a large sled and pulling this immense load over a path of lubricated log rails. This system would have reduced friction dramatically, allowing a coordinated human force to drag the stone giant across the island. Both methods point to a deep, practical understanding of physics, leveraging leverage, friction, and balance to achieve the impossible. The final act of this monumental effort was just as daring, levering the multi-ton statue upright onto its stone platform, the Ahu. Using a ramp of stones and a complex arrangement of logs as pivots and levers, crews would have painstakingly raised each Moai into its final, commanding position. This was not the work of a few individuals, but of an entire community united by a shared vision. In an environment with limited resources and complete isolation, this achievement stands as a breathtaking testament to human ingenuity and resilience. The Moai are more than statues, they are monuments to collective will, a silent answer to the question of what people can accomplish when they work together against impossible odds. Long before the first stone was laid at Stonehenge, a forgotten culture on the Mediterranean islands of Malta was engineering the impossible. The megalithic temples of Malta stand as a silent challenge to our timeline of history, their massive limestone blocks forming the oldest free-standing structures on Earth, dating back over 5,000 years. These are not simple stone circles, but complex architectural marvels with curved walls, paved courtyards, and internal chambers that echo the shape of a cloverleaf. Their construction required a vision that could see a finished sanctuary in a raw slab of rock, and the skill to make that vision permanent. To move these colossal blocks, the builders devised an ingenious solution. They placed stone spheres, carefully carved to a uniform size, beneath the massive slabs, creating a primitive but effective system of roller bearings. Teams of workers could then lever and push the stones along these rolling pathways, guiding them into their precise positions. Once a block was in place, the final act of lifting and setting was likely achieved with a system of wooden levers and counterweights, a patient application of force that turned raw strength into architectural precision. But the temples are more than just a feat of engineering, they are a stone calendar. Their doorways and internal passages are aligned with the rising and setting sun of the solstices, casting beams of light into the deepest chambers on the longest and shortest days of the year. This reveals a society of Neolithic engineers who are also master astronomers, weaving their understanding of the cosmos directly into the fabric of their sacred spaces. They carved spirals and animal figures into the soft limestone, a language of symbols whose full meaning is lost to time. These structures are a profound puzzle, a glimpse into a sophisticated spiritual and technological world that flourished and then vanished, leaving behind only these stone giants to whisper of a forgotten age of genius. Stretching across mountain ridges and plunging into valleys, The Great Wall of China is not a single wall but a network of fortifications woven together over 2,000 years. Its construction was a continuous conversation between human ambition and the rugged landscape, a project so vast it required the effort of countless individuals across numerous dynasties. The genius of its engineering began with a deep respect for local materials. In the western deserts, builders used what was abundantly available, creating sections of rammed earth, a technique where a mixture of earth, gravel, and clay was compacted between wooden forms to create walls of incredible density and strength. As the walls snaked eastward into rocky highlands, these earthen ramparts gave way to formidable barriers of stone, and finally, under the Ming dynasty, to the iconic brick and mortar facings we recognize today. This was sustainable engineering on a continental scale, using the very bones of the land to build its defense. The wall's path was never forced. Instead, master surveyors and engineers meticulously charted a course that followed the natural defensive lines of the terrain. It crowned mountain peaks, traced ridgelines, and plunged into steep valleys, using the existing topography as its first and most powerful line of defense. This was not just about saving labor, it was about creating a structure that was an organic part of the earth itself, making it far more stable and enduring. Upon this intelligent foundation rose the wall's operational nervous system. Watchtowers were positioned at regular intervals, always within sight of one another, forming a continuous communication chain. From these towers, sentinels could send messages using smoke signals by day or beacon fires by night, relaying information across vast distances at speeds that would have seemed magical at the time. These towers were not mere signal points. They were also fortified garrisons, storing supplies and housing troops, allowing small detachments to hold strategic positions against overwhelming forces. The wall itself was a meticulously designed combat platform. The walking surface was wide enough to allow the rapid movement of troops and carts, while the protective crenellations, the tooth-like parapets along the top, gave defending soldiers cover to fire from. Arrow slits were carefully angled to provide a wide field of fire while exposing the defender to minimal risk. Every brick, every stone was part of a cohesive defensive machine. The logistical effort behind this endeavor is almost beyond comprehension. Coordinating the quarrying of stone, the production of millions of uniform bricks, and the feeding and housing of an enormous workforce required an administrative machine of breathtaking efficiency. This was more than a military barrier. It was the ultimate symbol of imperial power, a statement written across the mountains that the empire could organize nature and humanity on a scale the world had never seen. It stands as a monument not just to keeping people out, but to what human beings can achieve when they work together across generations. Deep within a narrow desert canyon, a city emerges not from the ground, but from the living rock itself. The rose-red cliffs of Petra are not a backdrop, they are the architecture. The Nabateans did not build their metropolis, they revealed it, carving temples, tombs, and homes directly into the sandstone walls with a jeweler's precision. This was more than construction, it was a profound act of subtraction, a masterpiece of reverse engineering that required a complete understanding of the stone's character. Before a single chisel struck, these engineers had to visualize the final structure hidden within the cliff face. They would carefully select a section of rock, examining its grain and stability for any hidden fissures that could spell disaster. The most astounding technique was their method of sculpting from the top down. For a structure like the iconic treasury, workers were suspended from the cliff top, beginning their work at the highest point of the future facade. As they carved downward, they removed the debris from above, ensuring that falling rock would not damage the delicate, already completed work below. This top-down approach eliminated the need for scaffolding and transformed the construction site into a clean, descending workspace, a logistical marvel in its own right. But their genius was not confined to the cliffs. In a landscape defined by scarcity, the Nabateans engineered a paradise. They mastered the desert's most unpredictable and destructive force, the flash flood. Instead of fighting these torrents, they tamed them with a complex network of dams and diversion tunnels that channeled the violent water away from the city center. They then captured every precious drop in vast, carved cisterns and fed it through a network of ceramic pipes and rock-cut channels, creating a reliable public water supply that fed gardens, baths, and homes. This hydraulic system turned a barren canyon into a lush, thriving oasis at the heart of global trade routes. The city itself was a testament to adaptive engineering, its very existence a declaration that human ingenuity could flourish in the most challenging environments, finding abundance where others saw only stone and sand. These stone pathways were the arteries of empire, carrying soldiers, merchants, and information across continents. The Roman road was a marvel of layered permanence, built not merely to last a season, but for millennia. Surveyors would first chart a straight line across the landscape, an arrow of intent that ignored all but the largest obstacles. Then laborers dug a deep trench, the fossa, and began building upward from the earth. The first layer was a bed of small stones, the statumen, for basic drainage and stability. Upon this, they laid a thick mixture of sand and gravel, the rudus, which was compacted into a solid, unyielding mass. The next layer, the nucleus, was a finer concrete of lime and crushed pottery, creating a waterproof barrier. Finally, the surface was paved with large, interlocking polygonal stones, fitted so tightly that weeds could not find a purchase. The road was not flat but cleverly crowned, its center slightly higher than its edges so that rainwater would run off into drainage ditches alongside. This meticulous, multi-layered approach created a surface so resilient that many of these roads are still in use today, their stones worn smooth by 2,000 years of footsteps and wheels. Meanwhile, on the other side of the world, the Incas faced a different kind of challenge. Their empire was a vertical world of jagged peaks and deep ravines, where a straight line was impossible. Their solution was a network of roads that embraced the terrain with breathtaking ingenuity. They built stairways directly into cliff faces, allowing travelers to ascend thousands of feet. Where a gorge split the path, they wove bridges of woven grass. These suspension bridges were engineering marvels in their own right, with cables as thick as a human torso anchored into stone abutments. Each year, communities would undertake the sacred duty of renewing the bridge, a communal effort that ensured this vital link remained strong. The Incas also constructed way stations, known as tambos, at regular intervals along the route. These provided shelter, supplies, and fresh runners for the chasqui, the relay messengers who could carry a message from the capital to the farthest reaches of the empire in a matter of days. The Roman road conquered distance with unyielding straightness, while the Inca trail conquered altitude with adaptive grace. Both systems, however, served the same profound purpose. They shrank vast empires, allowing a single command from a central authority to ripple outward with astonishing speed, binding disparate lands together with nothing more than packed earth and carved stone. These ancient pathways remind us that long before the internet, the greatest network was the ground beneath our feet. From the depths of a 2,000-year-old shipwreck, a corroded lump of bronze and wood revealed a secret that rewrote history. The Antikythera mechanism, as it is now known, was no simple calendar. It was an intricate analog computer, a cosmos of interlocking bronze gears housed in a wooden case no larger than a shoebox. By turning a simple hand crank, a user could set in motion a miniature universe with dozens of precisely engineered gears calculating the complex dance of celestial bodies. This single device could predict the positions of the sun and moon, forecast lunar and solar eclipses, and even track the cycle of the ancient Olympic Games. The level of miniaturization and mechanical integration is staggering, with some gears thinner than a coin and teeth cut with a precision we would struggle to achieve without modern machine tools. This was not a tool for navigation, but for understanding, a philosophical instrument that modeled the very mechanics of the heavens according to the Greek worldview. Its existence implies a lost lineage of technological thought, a school of engineering and astronomy that flourished in the Hellenistic period only to vanish from the historical record for over 1,000 years. How many other ideas, how many other masterpieces of mechanics were lost to the sea or simply crumbled to dust? The Antikythera mechanism stands alone, a silent witness to a path not taken, a profound reminder that the spark of technological genius has flickered brightly in ages we have only just begun to comprehend. These immense stone blocks did not levitate into place. They ascended on engineered pathways of earth and ingenuity. The straight ramp theory suggests a single, colossal incline built directly against one face of a pyramid, growing longer and steeper with each new course of stone. While straightforward, this method would have required an almost unimaginable volume of material, a temporary mountain of brick and dirt just to build a permanent one of stone. A more elegant solution may have been the spiral ramp, a corkscrewing roadway wrapped around the pyramid's rising tiers. This design used far less material and provided access to all four sides simultaneously, but it would have created a dangerously constricted workspace for the teams hauling multi-ton blocks. The true answer might lie in a combination of both, a straight ramp for the massive lower courses and a spiraling one for the delicate upper reaches. Once a stone reached its intended level, the final act of placement was a ballet of leverage. Workers would have used wooden levers as long as tree trunks, inserting them beneath a block's edge. With a coordinated push on the levers and with timber cribbing stacked underneath for support, they could inch the stone upward, alternating sides in a rhythmic, patient lift. This was physics made tangible, the simple principle of the lever granting a small team of people the power to maneuver a weight that would otherwise be utterly immovable. Later Greek engineers would refine this concept into the trispastos, a simple wooden crane featuring a winch, a rope, and a pulley system that allowed a single operator to hoist heavy blocks with remarkable control. These were not machines of magic, but tools of amplified human effort, each one a testament to an empirical understanding of mechanics. The real miracle, however, was the human engine behind these tools. Moving a 2.5-ton block up a ramp likely required a team of 20 men, all pulling in perfect unison, their progress marked by the rhythmic beat of a drum or the call of a foreman. This was social engineering on a monumental scale, a logistics chain of thousands of workers, all coordinated with the precision of a modern assembly line. Experimental archaeologists continue to test these theories, building their own scaled ramps and attempting to move replica stones with ancient techniques. Each successful experiment is a quiet triumph, a glimpse into the practical, sweat-soaked genius that allowed humanity to build its dreams into the sky. What other simple truths of physics are we overlooking, truths that our ancestors knew by heart and hand? This profound respect for the environment shaped every aspect of ancient construction. These master builders did not see the natural world as an obstacle to be conquered, but as a partner to be understood. Their structures were conceived as extensions of the landscape, designed from the very beginning to work in seamless harmony with sun, wind, and earth. In the blistering heat of Mesopotamia, the solution was not to fight the sun, but to outsmart it. Houses were constructed with incredibly thick walls made from local mud brick, a material that provided superb thermal mass. These walls would absorb the intense heat during the day, keeping the interior spaces surprisingly cool, and then slowly release that stored warmth during the chill of the desert night. This was passive climate control engineered millennia before the invention of mechanical air conditioning. The very layout of cities was a lesson in environmental adaptation. Narrow, winding streets were not a sign of poor planning, but a deliberate design to create pockets of deep shadow, offering residents and travelers relief from the relentless sun. Far across the world, in the precipitous Andes, the challenge was a shifting, unstable earth. Incan planners demonstrated an almost prescient understanding of geology. They carefully avoided building on steep, unstable slopes prone to landslides, instead choosing stable bedrock or reinforced terraces for their settlements. They read the mountain like a map, identifying safe zones through generations of observation, ensuring their cities would not be swept away by the very ground they stood upon. This philosophy of using local materials was as much about practicality as it was about wisdom. Why transport stone for hundreds of miles when a perfect alternative lay just beneath your feet? Using materials sourced directly from the site or from nearby quarries drastically reduced the immense logistical burden of transportation. More importantly, these local materials had already proven their durability in that specific climate. A stone that had withstood a desert's wind and sun for eons was a safe bet for a building meant to last centuries. This was sustainability in its purest form, long before the word ever existed. It was a holistic approach that considered the entire life cycle of a structure, from the quarry to its daily function, creating buildings that were not only efficient and long-lasting, but that felt as if they had grown naturally from the soil itself. How many of our modern structures will be able to claim such a seamless and enduring relationship with their environment 2,000 years from now? That same ancient wisdom is now being rediscovered in laboratories and design studios around the globe. The structural genius of the past is not a relic, it is a living library, and modern engineers are eagerly checking out its volumes. Consider the enduring mystery of Roman concrete. For decades, we assumed our modern Portland cement was superior, yet it often crumbles in salt water within decades. Meanwhile, Roman piers have defied the Mediterranean Sea for 2,000 years. The secret, researchers have found, is not in a single ingredient but in a chemical process. The Roman mixture of lime and volcanic ash creates a rare crystal that actually blocks microcracks from spreading. When a tiny fracture forms in the concrete, it travels until it hits one of these resilient crystals, which then heals the crack. This self-healing property is a revolutionary concept that material scientists are now trying to replicate, creating a new generation of durable, sustainable concrete that could drastically reduce the environmental cost of constant repairs. It is a stunning realization that an ancient recipe may hold the key to building the resilient cities of our future. This influence extends deep into the earth, into the very way we design for instability. In Peru, the seismic dance of Inca walls has inspired a modern engineering principle called base isolation. Instead of trying to make a building rigid enough to resist an earthquake, base isolation allows the structure to move independently from the shaking ground. The building essentially floats on a system of flexible pads and bearings, absorbing the energy of the tremor much like the interlocking stones of Sacsayhuaman shifted and settled. This ancient insight that flexibility can be a greater strength than rigid resistance is now a cornerstone of seismic safety in the world's most active fault zones from California to Japan. The legacy is not only in materials and mechanics, but in the very soul of our built environment. Look at the facade of a modern courthouse or a grand library, and you will often see the silent echo of a Greek temple. The use of columns, porticos, and harmonious proportions based on the golden section creates a sense of order, dignity, and calm. We are, perhaps unconsciously, tapping into that ancient understanding that certain mathematical relationships are inherently pleasing to the human spirit, fostering environments of focus and civic importance. Even the way we manage massive construction projects owes a debt to the pharaohs and emperors. The organizational charts, the supply chain logistics, the specialized labor forces, all of these were pioneered on the plains of Giza and the roads of the Roman Empire. By studying how ancient cultures coordinated thousands of workers without digital tools, we gain a deeper appreciation for the fundamentals of project management, communication, and human collaboration. The past is not a distant country, it is an active partner in innovation. In an age grappling with sustainability and resilience, these ancient solutions offer a powerful reminder. True genius is not always about inventing something new, but sometimes about remembering what we have forgotten and building upon a foundation that has already weathered the test of millennia. This enduring legacy of stone and mortar is far more than a collection of ruins. It is a living conversation across time, a testament to a universal human drive to push beyond the limits of the possible. From the celestial alignment of the pyramids to the seismic dance of Inca walls, these marvels reveal a profound truth about innovation. It flourishes not in spite of constraints, but because of them. Faced with the immense challenges of their environments and the simple tools at their disposal, ancient engineers responded with breathtaking creativity and precision. They turned raw nature into a reliable partner, demonstrating that the most sophisticated technology is often that which works in perfect harmony with the world. Their achievements stand as permanent reminders of what we can accomplish through careful observation, deep knowledge, and collective effort. As we look upon these wonders today, we are not just studying the past. We are gathering inspiration for the future, learning from masters who understood resilience, sustainability, and beauty as inseparable parts of a single, brilliant whole. We would love to hear which of these ancient achievements amazes you the most. Share your thoughts in the comments below, and if you enjoyed this journey through the structural genius of the ancient world, please subscribe for more explorations into the great mysteries of history. Join us as we continue to uncover the profound and often surprising secrets of our shared past.